Hi, in this video, we're going to talk about entanglement. So in particularly, we are going to talk about an entanglement in the context of a game called the CHSH game. But before that, let me just talk about what's so different about entanglement. And well, we have learned about what happens when we measure a spin, and the spin could be, uh, let's say, in an initial state, and you measure in either the X, Y, or Z direction. And when you measure, let's say, two different spins, then you have results which are uncorrelated. The measurement output from measuring one of the spins is not related to the measurement output when you measure the other spin. But if you have an entangled state, for example, if you have a state which looks like this, so up, down, minus, down, up, over square root of 2. So this is an entangled state, and let's say Alice and Bob have one part of this entangled state. Then if Alice measures in any basis, and she gets an output +1, then automatically Bob gets an output -1. And this can happen in any basis. So this is a very curious and interesting part of entanglement. And it could also happen that Alice and Bob are separated by a long distance, and you will it from the rules of quantum mechanics, the observation of these properties of these spins are instantaneous. And this is bothered Einstein. This phenomena of entanglement bothered Einstein quite a bit. And in 1935, Einstein wrote a paper, and this is the well-known EPR paper. Um, and there he argued that this sort of violates the local realism aspect of nature, and therefore there must be something wrong in quantum mechanics. Regardless, we are not going to go into the philosophy of quantum mechanics, but rather look at it from the point of view of a game. So the same phenomena of entanglement can be visualized in the form of a game that we are going to study. All right, so let's look at this game. So this is a game called the CHSH game, and this the it goes by the names of the authors. So this is Clauser, Horn, Shimoni, and Holt. And they came up with this idea around the late 1960s, maybe around 1969. And the game is the following. And there is the idea of the game is to win the game using all possible classical strategies, and also maybe then reintroduce a quantum strategy and see if we can do better. So the game is the following. We have a referee, maybe who goes by the name Charlie, and there are Alice and Bob. And so the referee picks up two random classical bits, let's call them X and Y, and sends them to Alice and Bob. So X, uh, Y. So these are some randomly picked classical bits. And then Alice looks at her bit and returns back to the referee a bit, again, a classical bit. Let me call that AX. That depends on what bit she got. And Bob also returns a bit AY. right? Then that will depend again on his receiving y, right? And Alice and Bob win the game if the following happens, right? X dot y, where this is the usual and condition. Dot means and, so the bit of received by Alice anded by the bit received by Bob is equal to ax XOR ay. So this is the condition for winning the game for Alice and Bob. All right. So and of course, Alice and Bob are able to communicate prior to the game, say, and have a particular strategy. And let's say they could have a strategy like, if I receive 0, then I will always return a 0. If I receive a 1, I'll return back a 1, or any such strategy. They are able to also communicate before the game, but not after receiving their qubits. But they are able to have maybe a shared randomness, maybe shared randomness. And this means that maybe they share a, a classical probability distribution, and they are able to devise their strategy using this shared classical probability distribution. Now, it turns out that no matter what strategy Alice and Bob come up with, they are able to win this game with only 75% probability. So no matter what strategy of winning. Okay. And it turns out that instead of the shared randomness, if you have Alice and Bob share an entangled state, then the probability of winning using a quantum strategy, this winning probability goes up to 85%. Okay, so now let's look at some all possibilities of classical strategy. So I've already made a table over here. So classically, Alice and Bob are able to make 4 strategies, and that leads to 16 possible outcomes. So the first strategy is no matter what Alice and Bob receive, they always send back a 0, 0. The second is if Alice and Bob, whatever they receive, they always send back 1, 1. The third one is that they send the same bit as the input, and the fourth one is that they send the opposite bit as the returning bit. Okay, so let's look at strategy number 1, which is this strategy. Okay, so let's look at this. So if you look at the strategy number 1, then you are you have over here the possibility of Alice and Bob going wrong is 1 out of 4, and it is in this case. So this is the case where they receive 1 and 1 as bits, but of course x dot y is 1, but they return 0 and 0. So ax plus ay is 0. So they are wrong in one possible case. In the second case, when they always return a 1, again they are wrong in this one case, the final case. If they return back the same as the input, then actually it goes even worse. So yeah, they are wrong in all these 3 possible cases. And so if they return the opposite as input, so again they go wrong in these 3 possible cases. So the 2 columns on the right hand side are x dot y and ax XOR xy. So the best possible outcomes are in these two strategies, when they always return a 1 or always return a 0. So that is 3 out of 4 cases. So that becomes 75% of the time. And even if they have a sort of convex combination of these deterministic strategies, one could argue that you cannot increase this probability from 75%. So 75% is the best outcome in the classical case. Now, in the quantum case, Alice and Bob share. So over here, they, instead of the shared randomness over here, they share. So in the quantum case, this is shared entanglement. And this is, maybe let's go with this maximally entangled state, 0, 0 minus 1, 1 over square root of 2. Okay, so now if they share this entangled state, so the strategy is the following. Um, okay, so they share this maximal entangled state, and the idea is to apply a gate. So both Alice and Bob apply a transformation. Let me call that Ry of theta, which is equal to cos theta minus sine theta, cos theta. So depending on what bit they receive, they apply this transformation, and then measure their respective qubits and return the measurement outcomes to the referee. So in particular, if the following strategy is the most optimal strategy. So firstly, when they receive, so when Alice and Bob receive 0, then they apply the rotation Ry of minus pi over 16. So either Alice or Bob receive 0, then they apply this gate to their respective qubits, the shared entangled state, I mean. If they receive a 1, then they apply this rotation, Ry of 3 pi over 16, and then measure their respective qubits and send the information. Now, this particular rotation that they apply, suppose, so Ry of theta, this is a quantum gate, this applied to ket 0 is cos theta ket 0 plus sine theta ket 1, and Ry applied to ket 1 is minus sine theta ket 0 plus cos theta ket 1, right? So assuming that Alice and Bob apply, so the angles applied by Alice and Bob, let theta A be the rotation applied by Alice, and theta B be the rotation applied by Bob. So if Alice and Bob, so the rotations, of course, will depend on what bit they receive. And once they apply the rotations, their shared entangled state. So let me call the initial shared entangled state phi. Let me call this. So they share this entangled state phi AB minus, which is equal to the ket 0, 0 minus 1, 1 over square root of 2. Now, when they receive their particular bits, they apply the rotations to their local part of the shared entangled state. And the rotations, if I call them theta A and theta B, then this shared entangled. So phi A B minus, when you apply these rotations, one can see that it will go to cos theta A plus theta B, get 0, 0, minus 1, 1 over square root of 2, plus sine theta A plus theta B, and get 0, 1 plus get 1, 0 over square root of 2. So this will be the state, or the combined state, that when Alice applies Ry of theta A and Bob applies Ry of theta B to their respective parts of this entangled state. Okay, so now, and then they measure. So when they measure, AX plus AY is equal to 0 represents this measurement, and AX XOR AY equal to 1 represents the measurement. So the probabilities to get this outcome are cos square theta A plus theta B, and the probability to get this outcome is sine square theta A plus theta B. Now, when is AX XOR AY equal to 0? There are three cases when X dot Y is equal to, 0, that is when X is equal to 0, Y is equal to 1, or X is equal to 1, Y equal to 0, or both X and Y are 0. So this case, which means that both Alice and Bob rotate their bit. So if you look at this, when they receive a 0, they rotate by angle minus pi over 16. So this case, theta A plus theta B will be minus pi over 16 plus minus pi over 16. So this will be minus pi over 8. And in this cases, it will be minus pi over 16 plus 3 pi over 16. So is equal to pi over 8. Right? So Alice and Bob win with probability cos square theta A plus theta B, right? So probability of winning if AX XOR AY is equal to 0 is cos square plus or minus pi over 8, right? And that happens in these three cases. On the other hand, if when do Alice and Bob send this result, AX plus AY is equal to 1, when X dot Y is equal to 1, that happens only if X is equal to 1 and Y equal to 1. And that they would have rotated each by 3 pi over 16. So that's cos theta. So theta A plus theta B, sorry, theta A plus theta B will be theta A plus theta B will be equal to 3 pi over 8 plus 3 pi over 16 plus 3 pi over 16, which is equal to 3 pi over 8. And the probability of winning will be sine square 3 pi over 8. So this is when ax plus ay is equal to 1, this is when ax plus ay is equal to 0. But it turns out that sine square 3 pi over 8 is equal to cos square pi over 8. So the probability of winning is actually just 3 over 4 times cos square pi over 8, right? Because there are three cases when ax plus ay is equal to 1. That is when x equal to 0, y is equal to 1, x equal to 1, y equal to 0, or x equal to 0, y equal to 1, plus 1 over 4 times sine square 3 pi over 8, which is also equal to cos square pi over 8. So the entire probability of winning is cos square pi over 8. And this turns out to be 1 over 2 plus 1 over 2 square root of 2, which is equal to nearly equal to 0.85. So the probability of winning when Alice and Bob share entangled state and then apply a small rotation to the entangled state followed by a measurement, then the probability of winning is 0.85. The question to be asked is how did we get to this particular angles? And it turns out that over all possible strategies, these turned out to be the optimal angles. So it's an optimization problem to compute this particular angles. But the point is that if you use this particular quantum strategy, then you will win with probability 0.85. And well, can you do better? And it has been shown that the this cannot be the case. There is a bound called the Sillerson bound, which which shows that this is indeed the optimal strategy, and you cannot do better using shared entanglement strategies. Thank you.